Today's lecture is the second part or the continuation of chapter 4, total and effective stresses. We studied before total and effective stresses. I don't remember how many records, maybe we took two records or one record, but anyway, it was a part. We finished for total and effective stresses. We studied till we reached a section called stresses due to external loads. So we studied the internal loads in the soil, and then we started to effect of external load on soil. To study the effect of external load on soil, we said that we have many methods and many types of loads. Suppose you have a footing like this. It's an external load on the soil. We said that the external load may be point load, just concentrated load on the soil, and we said how to calculate using charts the effect. If I have a concentrated load here, I can calculate the stresses due to this concentrated load at any location of the soil, knowing the depth and the horizontal distance. I measure both and I apply in this chart to get the influence factor. I use this influence factor to get the stress due to P at this location. So this in case of point load. In case of line load, I have the same. It's the same shape, but instead of having P to be a concentrated load, no, it is a line load. So this line load will have an effect on this point. So I also can calculate this. And we took an example for this point. I have around it concentrated loads and a line load, and calculate the amount of stresses due to all of these loads on this point at a certain depth below the ground. We said that next time we are going to study uniform load. What is the effect of a uniformly loaded area on a specific location in the soil? So we took the concentrated line, now it is the uniform load. We have many cases for the uniform load. The first case is if I have a loaded area and this loaded area is square or rectangle. If I have a square or rectangle footing on top of the soil. There is a chart for this using the dimension. Here we have a factor called I4, which this is the one that we needed, and we have a factor called N. I use and I have a factor called M. So this is N and this is M, related to the dimensions of the loaded area compared to the depth. And so on. I substitute. Suppose I have, this is a loaded area, and I need to calculate the stress at this point. This point, it has a very important feature, which is the point should be at one of the corners of the loaded area. I cannot use this to calculate the stress at a point away from a loaded area or inside a loaded area. I only can calculate the stress at a point at the corner. Suppose that this is the loaded area, this is the corner, and I want to calculate the stress at a depth Z below the ground, then I can use this chart or this drawing. Suppose I don't have exactly, this is the loaded area. I want to calculate the stress here, away, very far from the loaded area, or just inside the loaded area. In this case, I have to make some kind of superposition of different loaded areas. I can divide my area into smaller areas so that I would have the location that I want to study at a corner of these locations. How come? At the beginning, suppose that I have this area, it's a loaded area, and I want the stress below a point inside. In this case, divide your loaded area into 4 loaded areas using these 2 lines. And you can start calculating the stress at point A due to this loaded area, and this loaded area, and this loaded area, and this loaded area. So the summation of 4 loaded areas, of the stresses due 4 loaded areas, will give me the stress, the cumulative stress for all of these loaded areas at the location. So instead of calculating the stress in the middle, I calculated the stress at the corner of this one, and at the corner of this one, and the corner of this one, and so on. So it is easy. So in this case, I will just add the results for 4 cases. Suppose I want to calculate the stress outside here. This is the loaded area, and I want the stress here at a point A outside. In this case, I will imagine that the loaded area covers all of this, and I will say, okay, point A is the corner point for the big area. So if I calculate the stress due to this big area, then I calculate more than the required stress, because I calculate the stress here due to this area plus this and this and this. I need to subtract them. So what I can do, but to subtract them, they should be corners. The point A should be a corner at any of these areas. So what I will do, I will say, I will take this big area. So this is the total. If I subtract from it this one, then I already subtracted this area. I need to subtract this small area, but I don't. This small area is not the corner of point A. So I will subtract from it this big area. In this case, this area in the middle, this one was repeated twice. Once when I was using this big area, and another time when I was using this big area. So the stress due to this was repeated twice. Do you follow me? Note, according to the Egyptian code, the point at which the stress will be calculated should be at the corner of the area. I cannot calculate the load except at any corner, any of the 4 corners you choose. But it should be a corner. So now, as we said, for figure 1, we will calculate, to calculate the stress at point A, I will subdivide the big loaded area into 4 small loaded areas, and I will sum the effect of the 4. In case of this, where I need a point outside, then I will use the big area minus this small area minus this small area, and then I will add this small area that was repeated, was subtracted twice. I only want to subtract it once, so I will add another one to substitute for what I have subtracted. Example: for the shown raft foundation, estimate the vertical effective stress increase at point A and B. This is point A and this is point B. The same that what we have said. We can just, for point A, I can just subdivide this big area into 2 areas. This area 1 and this is area 2. I get the effect for area 1. I add it to the effect of area 2. It gives me the effect of area 1 and area 2 at point A. So this is just you get the dimension x, y of the loaded area. For this loaded area, I will have 28. X is this area. Y is this area. So x is 8, y is 28. Z is the depth. What is the depth, the required depth? It is in the example. He wants it at 5 meter below. So 5 meter is given. This is Z. I'll just calculate M and N, use M and N, go to the curve, get the value here. Here, this curve, this is M, and this is N, and these curves has different values for M. So using the value of N with the value of M, I will just go horizontally, vertically from here till I cut the curve for M, and then calculate I4. Put I4, multiply it by the value of the stress. I will get the stress at the point where I need. This is very, very easy. The other case, I need at this point. In this case, I will have to do this matrix. I will divide I will have 4 areas. A1 is it is 36 by 22. 36 is the total of this. 22 is the total. So area 1 is the total area. Area 2 and area 3 is this area and this area. These are area 4 is the part that was repeated twice. I will get all of the values. I will get the value of M. I will get the value of N. I will get I4 for the from the chart. But here, instead of calculating the stresses and then adding and summing, no, I will just do the same for the I4 itself. I will take the value of I4. This is the first I4 I calculated for the big area. I will put it here. Minus I4 for the second area. Minus I4 for the third area. Plus I4 for the fourth area. This will give me the total of the total I, and then I multiply it by Q. If you would like to do it step by step, take this I, multiply it by Q, take the other I, multiply it by Q, and so on, and then apply summation and subtraction to the total stress. It's the same to end up with the effect of this. So now we said that uniform load, we had number A. It is a loaded area, square or rectangle. This we studied now. The other thing for uniform area is an approximate method. If I have a loaded area like this footing, and I want to calculate the stress at any point, okay, at this point, you take the load here. Any load on the ground does not go vertically in the ground. It has to spread. You never go vertically with your load except the shear strength of the soil is 0. So you will push. When you stand in water, you just go vertically down. Why? Because there is no shear in water. But when you stand on soil, you don't go vertically down. Why? Because the friction between the soil particles and the shear between the soil particles prevented you from falling down. So what happens is that your load is dispersed at a bigger distance below, and once it is spread below, it affects a bigger area. If this footing is here, it is affecting at this location, it is affecting the area below it. But if I tell you what is the effect of this footing at a depth Z below the footing, will it be the same? If it will be the same, it means that if I put a load on the ground, it will reach the other side of the earth, because load is not dispersed. What happens is that once the load goes down, it is dispersed on a bigger area till it is diminished, zero, because the load is constant and the area is increasing till I reach a limit that the load has no effect on the ground. So this is another way for calculating the additional stress of this load on any point. I take this load. What is the load? If I have here a load P, what is the stress here, Q? Do you know how to calculate the stress due to a load? Load over area. The load is P, and the area is the area of the footing. So load divided by the area of the footing, I get the stress. So if my point is just below the footing, then the stress at any point below the footing is this value, the value that you have just calculated. If I tell you no, I want the stress at a depth of Z, go to a depth of Z, disperse the load with an angle 2 to 1, spread the load with an angle 2 to 1. So now the load is the same, P will be the same, but the area here, it will be increased. Instead of having B by L, it will be plus Z, and L will be L plus Z, because the area below here increased compared to the area above here. So the stress here is what? It is P divided by B plus Z multiplied by L plus Z. What do we think about this method? This method, as it is called, approximate method. Why it is approximate method? Because it assumes that the stress at this point is the same as this point, is the same as this point, at this point, at this point, which is not logic, because in some cases the stress at the middle will be very high, and in some other cases the stresses at the edges are high depending on the type of the soil. So this method is approximate because it assumes that the stress at any level, at any point within my required level is the same. You remember here we were calculating the stress. Let's have a cross section if we can have here. We were calculating the stress at this point, at a point, but if was it the same here or the same here? No, it was different. Each point has a different stress, but in my case here, it assumes, for simplification, that all the points here have the same stress. So it is a method, and we use it in our design, but we have to know that it is an approximate method. There is another method called the Newmark chart for calculating the uniform load. Newmark chart, it was named after a scientist called Newmark. He derived a formula, and this formula he transferred it into a chart, and we can use this chart to calculate the stress under any shape. Not square, not rectangle, any shape, whether it is random shape. He can calculate the stress below any point in this shape. He gave us a formula, sigma z, which is the additional stress due to the loaded area, equal to 0.05 n. N is a number, multiplied by Q, which is the stress itself. Suppose you have take this L-shaped area. I want to calculate the stress at a point N within this shape at a depth of Z. Do you follow me? This is a little bit, you have to concentrate a little bit. I have an area, an L-shaped area. I want to calculate the stress due to this loaded area. It is loaded with a stress equal Q. But I want to know the effect of Q on a point below N with the distance of Z. Newmark prepared this chart. He tell you draw your area with a scale. He next to the chart he gave you something here, a distance called AB, and he said that this AB is equal to Z. It means that if you want to calculate the stress at point N at a depth of 5 meters, then this should be the scale which is equal to 5 meters. Suppose I want to solve this problem at a point below N with the distance of 5 meters. Then in this case, the scale of my drawing will be that this is 5 meters. So now we said that according to the depth that I want to calculate the stress at this depth. If I want to calculate the stress at a depth of 5 meters, in this case, Newmark chart, this area, this line A, B, it should be B here, A, B, this length will be equal to 5 meters. So this is the scale of my drawing that I should use. I should use this length. Suppose that this length is 5 centimeters for ease. This is, when you measure it using a ruler, it is 5 centimeters. In your calculation, you want a depth of 5 meters. In this case, I want a scale of each 5 meter is represented by 5 centimeters. So 1 centimeter represents 1 meter. So it is scale 1 to 100. So I draw my drawing on a tracing paper, ورقة شفاف, on just a tracing paper, and I draw my footing on top of it with a scale of 1 to 100, or each 1 centimeter represents 1 meter, and I draw my footing. Then I take the point where I want to calculate the stress. Suppose that this is my footing, it is an L shape, and I want to calculate the stress at point N, this one. Then I draw this on the tracing paper, I take the tracing paper, move it till I put this point N on the center. This is now the shape of the footing on the Newmark chart. Then I count the number of squares or four-sided figures below this footing. I count the number, suppose that they are 20. So I take this 20, I substitute it here for N. I know that the Q, which is the stress of my original footing, I'll multiply all of this together, then I get sigma Z. What is sigma Z? Sigma Z is the stress due to this footing below point N at a distance of Z. Okay, the stresses in soil present. This is another thing. We finished now Newmark chart and the 3 methods for calculating the surface area. Now I want to go into something called the principal stresses, or the stresses in general in soil. If you are standing on soil, your inducing vertical stress in the soil. Is it only vertical stress that is generated in this soil, or there is also horizontal stresses in other direction? There is horizontal stresses. How this happens? It happens when vertical stress is affecting any body. It produces, in any body, it produces horizontal stresses. To remind you with this, remember always two things. The first thing, the weightlifter, the athlete that go and carry very heavy loading to a certain height. He puts a belt around his stomach. Why? He's carrying vertical load. What will his stomach do? He's afraid that his stomach may be, his muscles may be torn away because of the vertical load. بالعربي بنسميها فتق، يحصل فتق. فتق ده معناه, it means what? It means that separation in vertical fibers of the muscles. Why this would happen? Because of vertical load. In columns, you put stirrups. You know what is stirrups in columns? Columns, it is put mainly, columns mainly carry vertical load. So when I put vertical load, I need vertical bars. Why do I put stirrups all around? Because due to vertical load, there may be horizontal loads. So I want to put stirrups all around. So this is what happens in soil. If you have vertical stress, vertical load, this vertical load will generate vertical stress and will generate also horizontal stress. Now, horizontal in which direction? Vertical, I know, vertical is in this direction. But horizontal, I have 360 degrees, all the direction. So usually, we take two perpendicular directions. So we say that we have sigma 1 vertical, sigma 2 horizontal in any direction, sigma 3 horizontal in the perpendicular direction to sigma 2. This will cover all the stresses in the soil. So we have, if I have an element in soil, it is affected by 3 stresses. We can look at this drawing. This is an element. This element is subjected to sigma 1. It's a vertical. But plus this sigma 1, I have sigma 2 horizontally and sigma 3 also horizontally, but in another perpendicular direction. This, if you have a cube of soil and this cube you subject it to sigma 1, sigma 2, sigma 3, then you are affecting all the faces of this cube. This will, because each one has, if I have sigma 2 in this direction, there is another sigma 2 in the opposite direction. Here, this is sigma 3 and this is also sigma 3, because is this element moving or stable? Am I speaking about a soil element that is moving from one place to the other? If I push this mobile, it will move. But if I tell you that I'm pushing this mobile and it is not moving, it means that there is an equal and opposite force in the opposite direction that is preventing it from motion. This is what happened. If you induce sigma 1 on the soil, there will be sigma 1 coming from the bottom to prevent the soil particle from moving, and whatever will be generated, sigma 2 or sigma 3 in the horizontal direction, they are both, forces are stable. These forces are not causing the body to move. It's not moving. It's just internal forces in the soil. So now we have sigma 1, sigma 2, and sigma 3. This is considering the stresses of the soil. But as we said before, we have soil and we have water. So there is water. But what is the difference between the stresses of water and the stresses of soil? The stresses of soil can be different. I may have sigma 1, sigma 2, and sigma 3, each one with a different value. But in water, if you have a stress, it is always, when I ask you what is the stress in water at a depth of 4 meters, you will tell me the stress in water is gamma water multiplied by the height of water. So at a depth of 4 meters, it is 4 multiplied by gamma water. In which direction? In all directions. The stress of water is always in all directions. So these are the stresses, sigma 1, sigma 2, and sigma 3. And this is the stress of water that is affecting any point at any with the same value. So if I come to define these stresses, I have sigma 1, which is the total stress at any point of the soil, which is sigma 1 is the vertical stress. Sigma 2 and sigma 3, we said that they are the horizontal. Sigma 1 is the major stress because it is the vertical load affecting the soil. Because of this vertical load and because of other reactions on the soil, I have sigma 2 and sigma 3 to keep my block stable at its place. So I have also sigma 2 and sigma 3. Usually, sometimes I may take sigma 2 and sigma 3 to be the same. In case of soil, usually we call it isotropic soil. Soil is isotropic. It means that if I have vertical load applied at one location, it will generate horizontal stresses. These horizontal stresses is the same in any direction. So sigma 2 and sigma 3 usually are taken equal to each other. If they are different, okay, they are different, we can calculate them. But I'm just now speaking about names. Sigma 1 is the vertical stress. Sigma, this is the major stress, it is vertical. Sigma 2 and sigma 3 are the horizontal stresses. This is the total stress. If I tell you what is the effective stress, we just discussed this at the beginning. If I have stress carried by the water, then I want to calculate the effective stress, then the effective stress is what? Is the total stress, and I have to deduce from it the part that was carried by water. You remember when we said that I'm now standing on clay. Clay includes water. It is saturated clay. It includes water. When I stand on top of the clay, my total weight is, say, 70 kilograms. So 70 kilograms is my total, this is the total weight. What is carried by water and what is carried by the soil? I don't know. I can assume at the beginning that 50 kilos will be carried by the soil, and 20 kilos will be carried by water. So the effective weight going to the soil is not 70, it's now 50, because water carried 20 kilos. As time passes, the 20 kilos carried by water will diminish. Why? Because water is going to percolate the soil and consolidation will happen. It means that water is going to seep outside the voids. So as water seeps outside, the soil carries more. If the soil was carrying 50 and 20 was going to the water, maybe after a while water will carry only 10 and soil will start to feel 60, and so on till all of the load carried by the water is 0 and the whole load is carried by the soil. So I just want to differentiate between two things: total stress and effective stress. Total stress is equivalent to your total weight. Effective stress is equivalent to the portion of the weight that was carried by the soil, not carried by water. So to calculate it, I have to, if this, as I said, 70 kilos, then this will be 70 kilos minus the 20 carried by water, so it will end up having an effective weight or effective stress on the soil due to 50 kilos only. Okay, so from this slide I want just to reach few points. In any particle of the soil is subjected to vertical load in both directions, horizontal load in two perpendicular directions. Vertical load sigma 1, horizontal loads sigma 2 and sigma 3. All of them are in equilibrium. The body is not moving, they are just cancelling each other. Sigma 1 from one direction, I have sigma 1 from the other direction, it cancels each other. But the body itself is under pressure. This small particle, it's not moving. It has load from one side and load from the other, but it's pressure. I need to calculate this pressure, because if imagine yourself standing and two of your friends, one pushing from one direction and one pushing from the other direction. You're not going to move, but you will suffer because they are squeezing you. So this is what is happening in the soil. The soil particles are being squeezed by vertical loads and horizontal loads. So this is what I need to calculate for the soil, because if I have soil that is squeezed and stressed, it will different than another soil that is not that squeezed. So this is important for us in future studies to understand what is sigma 1, sigma 2 and sigma 3, what is water pressure, so what is total and what is effective stresses. This is only what is important here. I will stop here because the next part of the lecture needs some kind of concentration. We'll go into shear stresses and more circle. I will just postpone this to the next lecture, because I don't think it will be a good idea to start it now in this condition. Thank you. See you next time.